In this video, I'm going to talk about how I use my multimeter in the process of troubleshooting audio circuits. If you're new to this channel, I deal almost exclusively with repairing Portastudios, that is multitrack cassette recorders. So although what I'm going to show is probably going to have some relevance, even if you're doing something completely unrelated like car electrics, it's going to have much more relevance if you're dealing with hi-fi separates, some relevance if it's, guitar amplifiers or power amplifiers, but really I'm mainly working with like low current, relatively low voltage audio applications. So I'll run the intro and then we'll get into it. Before we start, I just want to give you some kind of caveat about safety. At points, you're going to see me touching circuits with my bare hands. Now, I do have insulative gloves, that is rubber gloves so that the electricity can't get into. Most of the units that I work on, a lot of them have external AC to DC transformers. So the linear or switching power supply isn't even in the chassis. And those units where the transformer is inside the chassis, I know where the AC is coming into the unit, and obviously I'm not going to be doing too much near there. I'm going to be very careful about putting a screwdriver, certainly my fingers, anywhere near where the AC comes in or near the primary side of the transformer. But generally speaking, the sorts of units that I am used to working on, once you get to the secondary side of the transformer, the currents and voltages are so low, the chances of me getting an electric shock by touching the circuit board are almost nil. It's much more likely that a static charge in my body might damage a microcontroller chip than anything that's in the circuit would damage me. If you're not sure about electrical safety, loads of people have got videos about that. I'll maybe try and find a couple and put links to that in the description, but make sure that you know what you're doing, or if you don't, then for your own safety, go ahead and wear insulating gloves when you're doing this kind of testing. I do not want to be held responsible for anyone getting an electric shock, okay? So, next thing to talk about is the cables that I think you should have if you're going to use a multimeter to try and figure out what is faulty about, your hi-fi separate or your Tetrakan Portastudios, something like that. So, your meter is going to come with a pair of probes like this, where it's like a little pen stylus with a naked metal tip, and we are definitely going to be using those. I also like to use cables like this, which have a banana connector at one end and a really strong, quite large crocodile clip at the other. That's because there's situations where I want to have at least one hand free. So later on I'll be doing things like using the casing on a fader, clipping that on, because that's going to be like circuit ground for a mixer board. That allows me to plug in this one and start taking voltage readings or whatever, and I've still got a hand free to move things around, turn up faders, turn down faders, this kind of thing. There are also going to be situations where I'm going to want to test, for instance, the continuity of a wire. I want to check whether a cable is broken, and so I will be clipping onto DuPont wires like this, so that I can then insert those into headers. So here's a scrap wire. Let's say that that's actually connected to something, and I think that there should be electrical continuity between the red and yellow cable here. Then what I can do is take the DuPont wire and plug that in. And then the female to female DuPont cables, these ones, they're handy because then I can slot this on here, and then I put the other end over a pin on a header on a circuit board. This is just a connection issue. I'm not showing you how to troubleshoot anything at this point, but you've got to imagine if you only had the original probes that came with it, getting both of those onto these little pins here and making sure that they don't touch each other or adjacent pins, I mean, that's a real pain in the neck. So I find that having these banana to alligator clips and male to male and female to female DuPont cables on hand, that's going to make it much easier to use your meter. In terms of shopping for these things, this is the meter that I've used for a while. It's an X-Tech, which is like not the cheapest brand, but not the most expensive brand either. I'm trying to see exactly what the model is. I'll put it up on the screen. I've forgotten. What I'll also do is I'll put some affiliate links where I get a tiny little kickback if you use them to buy these different items from, you know, Amazon and eBay and this kind of thing, if you're not sure exactly how to search for them. But I paid maybe £30 for that second hand, maybe less. I think a pair of these was a few pounds. A pack of about 10 of these was like £1. A pack of 10 of these was £1. So we're not talking about a huge investment here. And yeah, these stylus style probes came free with that. You can get meters that are a lot more expensive than this. I think some of the Fluke ones are like £100, so like $150. You can also get incredibly cheap ones from, you know, Banggood and AliExpress and all this kind of thing. So what's a minimum standard for this? And at this point, I'll talk about which of these settings I actually use and which I never bother to use. I'll be honest, I never really measure current. For a start, there's Ohm's law, so you can kind of infer what's happening with the current from voltage and resistance readings. And it tends to be a hassle. The way that you would take the reading, the entire current has to pass through this. That's not always easy to achieve. And really, if there's a problem with current, then something's going to overheat and you'll smell it or you'll see it burn. Or if you hover your hand above it, then you can feel that it's hot. So I don't find that that's very useful. The capacitance, well, you could measure capacitance. To be honest, like for a lot of transistors and for capacitors, I find something like this is much more convenient. You take them out of circuit, put them in there, you turn it on, and it'll tell you, you know, what the value is. And it's obviously saying it's got no part there. Diodes, transistors, capacitors, I tend to use that. So which settings on here do I use a lot, and therefore which ones should you want to be included with your meter, whichever one you're shopping for? Well, the diode tester, I definitely use that. There's a little symbol here. On this one, you cycle through the mode button. So we've actually got diode tester, there's resistance testing, there's continuity and capacitance. So the diode tester, the continuity tester, and the resistance tester, I use those. Measuring AC voltage, yep, use that. Measuring DC voltage, yep, use that. This HZ percentage, that's a frequency counter. So a frequency counter you definitely need. It can be handy to have a cheap oscilloscope. I think this costs maybe £15, and that will also count frequency. So at one point I had a different meter and this didn't have a frequency counter, so I was using that for frequency counting and for getting a visual look at AC and DC voltages. So if you had one of those, then strictly speaking you don't need the frequency counter, but that's useful. And then it measures temperature. Again, I find if things are drawing too much current and they're hot, then you can usually, there's smoke or at least some odor. You can see things start to heat. Circuit boards look charred. If you hold your hand over it, then you can feel that it's hot without actually touching it and burning yourself. Continuity tester is essential, but I mean, I think any meter will include that. Likewise, the diode tester, measuring resistance, measuring two kinds of voltage. That's really what I'm using. In case it's not clear, I'll just show you how to plug the probes into this. It's going to vary a little bit depending on what meter you've got, but usually you'll have 3 sockets, and there'll be one in the middle that's labelled as COM. You'll usually have black around it. And that tends to be where you put the negative probe. So like, there's nothing different about these 2 probes, these pen style probes that came with the unit. Like, they're just wires really in a convenient pen-like format. So you could plug them that way around and it's not going to do anything terrible. But I normally like to keep myself right where the red one is what I'm attaching to, like the positive, and the black one's what I'm attaching to negative, you know, to circuit ground usually. I suppose ideally these banana to alligator cables I've got would be red and black as well, but I just, you know, put the blue one in common and the yellow one into this rightmost socket. So that socket is for voltage readings, resistance readings, frequency counter, everything really. We've got this separate socket over here, which is if I wanted to measure current up to 10 amps, which is a lot of current. As I've mentioned, I don't tend to actually measure current very much. Maybe I haven't mentioned it yet. I'm shooting all these sections out of sequence, but I will explain why I don't really tend to actually measure current later in the video if you haven't already heard that explanation already. So I don't really worry about this at all. And then in terms of which way round these should be, for resistance, it doesn't matter. Say there's a resistor there, I can measure it that way round or that way round. The resistance reading is going to be exactly the same. For AC voltages, and I'll explain why I don't actually use a meter to measure those much anyway, it doesn't matter because the whole point of AC is that it's going between positive and negative voltage all the time. I mean, if you hooked your oscilloscope probes the wrong way up, then it would kind of flip the image that you saw on the screen. So a wave that should look like that would actually come out looking like that. That would be a polarity flip if you got the meters the wrong way around, but it would still work. And if by accident, you know, you plug the red and the black one into the wrong sockets in these, or you put the red probe on circuit ground and the black one where your positive voltage should be, say you're trying to measure the input voltage for a active component and it should be 9 volts. All that would happen there is that the voltage would say negative 9 volts instead of positive 9 volts. Now, the place where you need to be a little bit careful with that, the sort of circuits I look at, operational amplifiers, will quite often have a positive and a negative power input. They need that in order to amplify AC signals, because AC signals will swing from positive to negative voltage. So I might mistake the positive and the negative voltage input on an operational amplifier if I had these the wrong way round. I mean, I suppose in summary what I'm saying is don't sweat it too much. Like, I can't think of a situation where you would really blow something up by getting these the wrong way around. It's just not that big of a deal. I did wonder whether to include a theory section in this video, because I could have just referred you to the hundreds, if not thousands, of articles and videos that are all over YouTube and the internet for things like, you know, Ohm's law and the difference between AC and DC, or just assumed that anyone watching this knows that. And the reason I have, at the end of shooting most of the examples of how to use the meter, decided that I will do a little theory primer is that most of the material that's out there is geared towards physics students, electrical engineering students, and would-be circuit designers. And these tutorials that are geared towards these sort of people contain a lot of very valid and interesting information. But that information and the mathematical worked examples, that's not only not particularly relevant to those of us who just want to get some stuff fixed, it can actually be a bit of a distraction. Like, I spent the early stages of learning this myself, seeing things like Kirchhoff's laws and these kinds of calculations and trying to shoehorn them into my technician's practice, you know, my repair person's practice, whatever you want to call it. And if someone had explained to me that all this stuff's very interesting if you're one of these people, but actually not very relevant if you're one of these repair people, then that would have saved me quite a bit of time. My perspective as somebody who wants to repair something is pretty different to a physics or electrical engineering boffin or a circuit designer. Generally speaking, I'm going to assume that the circuit that I'm working on has been well designed. Like, I work on Tetrakan Portastudios and similar things, and these are large Japanese and American companies with big research and development staff, and, you know, they probably spent millions of dollars or yen or whatever back in the day developing these things. So we can assume that when they left the factory, they'd already been through a pretty rigorous troubleshooting process by the people who had designed them. The reason that they're faulty when they come to me is because some of them are up to 40 years old, that's age, or they've been neglected. Someone's dropped it, someone's put the wrong power supply into it, someone's spilt a drink on it. So that's like user neglect. So we've got a good, well-designed circuit that has a fault somewhere, and we just need to find out where that is. So the first thing to talk about is the difference between AC and DC. AC stands for alternating current, and the symbol for it is usually a sine wave. I'm going to give you a couple of analogies about the differences with AC and DC about electrons in a wire, and I want you to take them with a pinch of salt. These are like convenient conceptual models to think about the difference. I think at a level of physics, what I'm going to say is probably like dubious, if not outright wrong, but it's a good enough way to think about it so for you to understand roughly what's going on. If you think that there's this tube called a wire and it's got these like balls in it that are called electrons, with AC, then those electrons are kind of vibrating back and forth, and the energy in them is to do with the vibration rather than to do with those electrons going in a direction. AC is used to transmit power over distance, so when you're plugging something into a wall in your house, it's AC that's coming out of the wall. It's also used to transmit analog signals. So for audio, because that's what I work with most of all, the sound waves end up being represented by a sort of wiggly line of voltage. That's roughly how it works. Whereas DC, which is direct current, which is usually represented by a complete line with dashed lines underneath it, we think of those electrons in this pipe and they're all moving in the same direction. You know, one of the things that's faulty about that analogy is that I gather that it's actually the charge of the electrons that moves more than the actual electrons themselves, but I'm not going to really go into the physics of it. Within a circuit, it's usually direct current that's used as a power source, so active components, things like LEDs that are producing light, LCD display screens that are showing an image, the motor that's turning your Portastudios cassette, the operational amplifier that's making the voltages louder within the mixer. These are all powered by DC. It's also used for signals, but it's digital signals. So you can turn the 5-volt signal on or off, and that acts as a control signal. I mean, Morse code would be an example of digital signal. You know, it's on or it's off, dash dot, dash dot. The microprocessors in a circuit will communicate with each other in a similar way. Now, the thing that's confusing about AC/DC is it's not either or. Actually, both of these kinds of electricity can exist in the same wire, which I find kind of hard to get my head around when I first learned it, but you know, just accept that that is true. Right, Ohm's law. This is something that you can find a gazillion different tutorials on, and usually those tutorials will involve someone, they've got like a battery. That's a symbol for a battery, and you know, there'll be some like components. You know, I think that's meant to be a light bulb, and there'll be some, you know, values. So this is 5 ohms, and this is 2 ohms, and this is 9 volts, and they'll show you how to calculate current and stuff. And it's a very interesting mathematical proof. It's very valid. It's very important, and I just don't use it. I just don't do those calculations when I'm trying to fix stuff. Or if I do, it's a guesstimate in mental arithmetic. It is very important to have a like intuitive understanding of the concept of it, which is basically there's this codependency between resistance and current and voltage. Don't be intimidated by what you're seeing just now. I just want to go over this as quickly as I can. What are these 3 properties before I kind of explain them in a more digestible water analogy? V stands for voltage, which is measured in volts. Shorthand for that is a V, and it's like pressure. I, that's current. It's measured in amps, which is A, which is like amount of water. And then R, which is resistance, is measured in ohms. The symbol for that is, I think, is that an Amiga? Yeah. And that's almost like the size of the pipe that the water is going through. And I was taught the mathematical part of it if you're interested in this sort of triangle. So V at the top and I and R at the bottom. Because, you know, if you imagine that's like a dividing line, that's a dividing line, that's a multiplication sign. So you end up that V equals IR, so voltage equals current times resistance. Current equals voltage divided by resistance. Resistance equals voltage divided by current. If you just don't know any algebra at all, don't sweat it. Think of it like this. Imagine there's a set amount of water coming out of a tap or a pump, right? So I'm going to draw a tap, but you've got to imagine this is maybe a pump. Faucet, if you're in America, I believe you call this. I call it a tap. Now, if that's just coming out of a hose, And the water is just going to drip down here. But if we make this into some sort of like Karcher pressure nozzle, then we've got like really powerful high pressure water. So what's happened there? The current remains the same, but by increasing the resistance, we also increase the voltage, right? By making the pipe smaller, we also make the water pressure higher. Same sort of idea, but imagine this is 10 feet tall now. It's a massive pump with a massive amount of water coming out, and you've just got this tiny little hose here. And that's going to be like really high pressure. That's meant to be high pressure because there's more current, but the resistance has stayed the same. Therefore, the voltage is higher, the pressure is higher. Now, the current, the I for current in that, I don't tend to measure that much with a multimeter because an external power adapter like this, I can assume that that is producing adequate current for the system that I'm trying to troubleshoot. Or if it isn't, then I can use DC voltage and resistance readings to diagnose and troubleshoot that. So really, I'm only concerned with the voltage and the resistance parts of that VIR codependency. At various points in this video, you're going to see me testing components out of circuit or suggesting that that is good practice. To understand why I'm suggesting that, why it's good practice, we need to think about how Ohm's law relates to parallel circuits. So if we go back to our tap and hose analogy, that's meant to be a tap. Here's our hose. But now this hose has got two ends, and one of them's got, this is meant to be a Karcher, high pressure nozzle. If we were doing some tests on how much water was coming out of there, or how high pressure the water was coming out of there, without realizing that there was this big end to the hose here, then we would get completely the wrong figure for how large this aperture is. Because basically, if the water's coming out of here, a lot of it's coming out of this big hole at low pressure, and much less of it is coming out of this small hole at a higher pressure. And it's kind of the same thing with a circuit. So if we've got this DC input, and there's a resistor here, but there's also a resistor here. And, they're both going to ground. Going to ground in that way just means that there's a circuit back to, like, the negative input. This is the positive input of, like, a battery there, let's say. Another way of drawing the same thing. If I test the voltage between the negative pole of this battery and this point here, without realizing that that's there, then I'm going to completely miscalculate the value of that resistor. I know that's not a very detailed example, but this is the conundrum that we're in when we're trying to measure resistance and voltage around components when they're still in circuit. I want to quickly draw your attention to the fact that circuits has an S at the end. I watched an interesting video by a guy called Daniel Sullivan, who I think is a college professor teaching people to do car electrics. His videos are very good, and he makes the point that there's no such thing as a parallel circuit. There are only parallel circuits. Like when I did that example, really there's two circuits. There's one that goes from DC power source to ground through this resistor, and there's one that goes from the DC power source through this resistor to ground. There's two parallel circuits being represented there. Now, if you get the schematic for anything interesting or at all complex, so in my case a Portastudio, what you're going to see is several pages of diagrams and umpteen different connections to ground. Each one of those connections to ground represents a different parallel circuit. So like a schematic is a system of parallel circuits. And so it's very difficult in the middle of that to be absolutely sure when you're measuring something in circuit that there isn't a parallel path. And if you take readings when things are still in circuit, those readings can be off. By the way, when I'm saying out of circuit, what I mean is you desolder the component from the printed circuit board and test it separately. If you've got a component that's only got like two legs, like a resistor, you can get away with desoldering just one leg. Likewise, a capacitor that's only got two legs, you could desolder one leg. Something like a transistor, because it's got three legs, it's not practical. Desolder two and leave one in. You normally just desolder the whole thing. Integrated circuits. Your little black microchips, they can't really be tested out of circuit. It's impractical. I mean, I deal with operational amplifiers, which are used as voltage amplifiers within the mixers and tape amplifiers of Portastudios, and they really need to be tested in situ. What I do there is use the audio probe to see what the signal is like going into and coming out of the operational amplifier, and then I can also test what the voltage is on the power inputs. Usually the parallel circuits that power an active component, they've got very few other components on them. Like if you look at the schematic, it goes from the power source, let's say that's a voltage regulator, directly to the input of your operational amplifier or whatever, without there being any kind of parallel circuits or extra components. So you can usually figure out if an op-amp's getting power and see whether it's processing its signal properly. If it isn't, then you would desolder that and just replace it. Having first troubleshooted any more easily diagnosable and understandable components surrounding it. Another aspect of Ohm's law that we need to talk about is how they affect voltage dividers. We need to talk about that partly because it's a precursor to understanding voltage drop, which I'll talk about in a minute, but also because voltage dividers are a very common pattern in schematics. So if you're going to be reading schematics, then we may as well quickly talk about those. So I talked about the sorts of examples that we often see in maths and physics theory heavy tutorial videos about this. So you'll have a circuit something like this. There's a battery, there's a resistor, and another resistor. And that connects back to ground of the battery. Let's say for argument that this is a 2-volt battery and this is a 1 ohm resistor and this is a 1 ohm resistor. One of the things that Ohm's law tells us is that the voltage is proportional to the resistance. That's what the mathematics says. I won't prove it. Go and watch other videos for that. But what that means is if I connect the black negative probe to the negative terminal of the battery, and then I put my red probe here, I'm going to see 2 volts. In an ideal circuit where these connections don't have any resistance, that is. And then if I put the red probe here, I'm going to see 1 volt, and I'm going to put it here, and I'm going to see 0 volts. So, because these are equal, half the voltage drops across this resistor, and half the voltage drops across this resistor. And for a schematic point of view, that kind of thing's important, because maybe there's a junction here, and then, we've got a transistor here, just enough current here so that this stays open, like the way that a car would idle even if it's not moving anywhere. If these values are different, say that's 9 volts, and that's 5 volts, and that's 5 volts, then my voltage measured from here to here, I'm going to get a reading of 9 volts. Here I'm going to get 4.5 volts, and here I'm going to get 0 volts. Now actually here I'm going to get slightly less than 9 volts because actually these traces or shielded wires or whatever this line in this drawing represents will have a little bit of resistance, so they will drop a little bit of voltage. So that's maybe like 8.9 volts. You're going to have very little voltage drop there, about half of it to there, and then you're going to be quite close to 0 volts here, and you would have definitely 0 volts if you actually touch the probes together. If this was 12 volts, this was 8 ohms, and this was 4 ohms, then I'm going to be able to read 12 volts like this. And it's going to drop down to 4 volts there, and it's going to drop down to 0 volts there, because like 2/3 of the voltage drop is happening there, and 1/3 is happening there, because this one's twice as much resistance as that one. So then I could take a line out here, and that would be 4 volts. And maybe that's going to light emitting diode, because 12 volts would ruin it, whereas 4 volts is enough to make it shine as brightly as we want to in this circuit. When I was plugging values into there, I was plugging like, really convenient values. It's really easy to do mental arithmetic on. You might use a calculator or do some written down calculations if those numbers that I was providing you weren't so convenient. But as I said earlier, I don't actually find myself doing those calculations. As long as I understand roughly what a voltage divider is and recognise it as a pattern in the schematic, then that's good enough if we're just wanting to fix stuff. So now let's think about voltage drop. It's a measurement you'll see me take later on in order to figure out whether semiconductors like diodes and transistors are healthy. So we may as well know what the definition is, but understanding this a little better again gives you that intuitive way of understanding electricity. So earlier I gave this dubious analogy that if a wire's like a tube, electrons are like balls in that tube, and they're all going from the positive pole of a power source to ground. Let's think of it another way. The power source is almost like a spring, like a pinball machine or something, and it's giving a ball energy. And when the ball goes along the ground, friction is taking a little bit of its momentum away, but not much. But then later on, it hits a domino. That's meant to be a domino. Looks like, I don't know, like a really fucked up snowman, but it's meant to be a domino. So it hits this domino and that slows it down a lot. So it might continue in this way, knocking over more dominoes, doing more work, right? So until eventually it comes to rest. Similarly, if we've got a DC power source, and so it goes through connectors. The DC power source is giving the electrons energy in the form of voltage. The electron passes through the cable, losing a little bit of energy, but then when it hits, I don't know, let's say it's a motor. So this circle with an M in it represents a motor. Then it's doing work. This is a load, and so it dissipates a lot more of its energy before it eventually goes to ground. So in both of these scenarios, we've got something that's raising something to a high level of energy, loses a very little bit through friction here, just a very small amount of resistance in the connecting wires in this circuit. But then when, in the case of the ball, it hits the domino, in the case of the motor, it's doing work on a load, then a lot more of that energy drops, and then eventually gets back to the same point that it started when the spring lifts the ball from being at rest to moving. The battery lifts the electron from having 0 volts to 9 volts, whatever. So that idea that the electron loses energy as it goes through resistors does work in loads. A load could be a motor, could be a light bulb, could be a loudspeaker, and then finishes up at ground. That is voltage drop. But I think the important takeaway from all that is that the voltage that comes from a power source is potential energy that can be used to do work in a circuit. So let's tighten that definition of voltage drop up a little bit and relate it to what we're going to be doing with the multimeter and other tools. Voltage drop can be defined as the energy used by a component when current flows. What's a practical way that we're going to use that fact? Well, semiconductors have a predictable voltage drop. And so when you take them out of circuit and the little current that's coming from your DMM passes through them, there is a correct response if the component is healthy. And if you get a different result, that tells you that the component isn't healthy. And that's a diagnostic tool. Next point, all the voltage drops in a circuit add up to source voltage. That's worth remarking on because if you're naive, as I was when I started using my digital multimeter and trying to figure all this stuff out, I was thinking, how come the schematic says that it's like a 9 volt power supply, but I'm seeing 8.732? For a start, sometimes they're not perfectly producing 9 volts, but if they were, you still wouldn't read 9 volts because the probes themselves have a little bit of resistance, wires have a little bit of resistance, the lands and traces on a printed circuit board have some resistance. Anything that has some resistance has some voltage drop, so that's why you're not seeing perfect round numbers when you're doing your probing with your meter or whatever. And so hopefully that's reassuring to you and you're not going to worry about it. Last thing, connectors should have low voltage drop. Otherwise, they steal energy from active components. So again, remember that we're trying to fix things that are well designed, but they're old or they've been neglected. And so one of the things that's like really common is a wire will get a shuggle, and so it'll actually break completely, or it won't be fully conductive. By not fully conductive, it's almost like there's a resistor in that wire. And so if you test a wire and it's got like quite a high voltage drop, that tells you that it's a bad wire and it needs to be replaced. Again, I draw your attention to the fact that we can use resistance or voltage measurements almost interchangeably because of the way those two things are related by Ohm's law. So actually, for testing whether connectors are bad, wires are bad, that kind of thing, I usually use the continuity tester, which is just a resistance test that beeps if it's below a certain level. So if I touch two wires and I hear the beep, then I know that the resistance in there is below 50 ohms, and it'll actually show me on the screen what the resistance is. Actually, 50 ohms is a lot higher than a wire should be. But anyway, I'll get into that later and show you that. So in practice, how am I actually using the probes? This here represents positive and negative output of a DC power supply, and it's going to an active component here. I've chosen to draw a DC motor. And as I said earlier, you're not going to see a simple schematic like that. This is going to be one of multiple parallel circuits in a much more complicated schematic. And so I'm going to put my black probe on circuit ground, and I'll talk a bit more about circuit ground later in the video. And I'm going to put that there. So if this is like a 12 volt motor, then I want to see a reading something like 12 volts there to know that that's getting enough energy. I could measure voltage drop here to make sure that it's a low enough voltage, which shows that the resistance of the connectors leading into the input of the motor are low enough. I could also use a continuity tester, see if that's beeping, see whether that resistance is low enough to indicate that this is a healthy connection. I'm more likely to take a voltage drop reading on components out of circuit. So say I've removed this diode from circuit, and I would test it this way and then this way, and there are characteristic readings that I should get. Like I should get infinite resistance in one direction and a drop of about 0.6 volts in the other. If I get those results, then the diode is healthy. If I get different results, then the diode is unhealthy. Or I could just measure resistance in either direction. This could still be soldered in one end, but really I want to have disconnected one of the leads in order for the readings that I'm taking there to be trustworthy. Just to give you a slightly more practical example that actually features a schematic, this is the input amplifier PCB assembly. So basically it's a mixer channel from a 244. So we can see that this is ground, this thicker line. So each of these places where ground branches off to something else, that represents another parallel circuit in a way. So let's say, for argument, I thought that this operational amplifier here might be turned off, like maybe it's not getting power or maybe it's faulty. So I want to take a reading there to check that it's getting power. So you can see there's a plus 12 volt input here, so I would find the corresponding pin. I probably need to check the specification sheet to just see exactly where that positive input is for plus 12 volts. But let's say for argument it's pin 4, so I'd find pin 4 on the corresponding integrated circuit and I'd put the plus pin there. But well, where do I put the black pin? Well, actually I can put it at any of these ground points. So I could find R1110 and make sure that I had the black pin the opposite side of it from this capacitor C107. It could equally be here, it could be here, if I can easily identify that capacitor and that resistor, as long as I'm this side of this resistor, I could put my pin there and that would still be a reliable reading. So if I did that test there, then I would expect my meter to say something quite close to 12 volts. It might be a bit less because of the voltage drop in the traces that are leading from the power supply to this pin of the op-amp, but so long as it's pretty close to 12 volts, I'm good. If it's 0 or it's a lot less than 12, then maybe I've got a problem with the connecting wire that's meant to be sending power to this operational amplifier. Maybe there's actually a fault with the power supply. I want to give you a little bit of context why, when we get to the practical examples bit of this video, you're going to see me use the AC voltage meter so little. I told you that the power that's transmitted to your home is done so via AC, whereas the power that's used within most small circuits like I work on, like Portastudios, the power source is DC. So a conversion needs to take place. In my case with Portastudios, a lot of the time, that conversion from AC to DC is done in an external adapter like this. So I don't even need to deal with the AC power. In some larger units, then you're going to have, I'll try and draw this like, God, this already isn't going well, but there'll be like a transformer and some large capacitors and, some diodes, or there'll be a bridge rectifier. And that's called like a linear power supply, an analog power supply. But even if I've got one of those, I tend to use, I'll explain it a little bit more later on, but I actually diagnose and troubleshoot the linear power supply using DC voltage readings and continuity checks anyway. I told you that AC is good for analog signals. So in my case, I'm working with stuff that's audio. So the sound that's going into the mixer to be recorded on tape or coming off the tape to be reproduced via speakers or headphones, that exists within the circuits that I'm working on as AC, alternating current. But if I try and monitor that using the meter, because the signal is at different levels at different points of the circuit, like it's very small when it comes in on a microphone or off a tape, but it's much larger when the mixer is equalizing it. And also because the musical material itself tends to vary in volume, like there'll be loud and quiet parts, and instruments like snare drums are loud and quiet, whereas instruments like violins are a consistent volume. It's very difficult to use a digital multimeter or even an analog multimeter to analyze what's happening to that audio signal. In the case of the DMM, you're going to just see a flickering screen with like the numbers changing. For those situations, I'm actually not using a meter at all. I'm using an audio probe. Now, an audio probe isn't something you can buy. I mean, there are some commercial ones, but they're few and far between. It's hard to go on eBay or Amazon and find one. It tends to be something that you make yourself. Think of it like a stethoscope that the doctor uses to hear what's happening, to your fluids in your body. Really what I'm doing is picking up the AC audio signal at a certain point in the circuit, and then I'm amplifying it with an external amplifier. So in my case, this is an old probe. In there's a capacitor because that will stop any DC from hurting the speakers of my external amplifier. So, this is where I put the positive. I attach this to circuit ground, which is something I'll explain in due course. And then I plug an RCA to RCA cable into this socket, and the other end goes into the amplifier. So basically I can touch this and actually hear the sound. So for instance, there's an input over here and an output over here. And it's going through, I'm just going to use boxes. 4 different components. I've established that the sound's getting in, but it's not getting out. So where is it blocked? So then I can go in, imagining this is attached to circuit ground, and I touch here and I hear, ooh, okay, it's all right, the signal's here. It's like, ooh, it's a bit louder. All right, that's fine. Ooh, it's fine. Oh, there's nothing there. What about coming out of this one? Oh, there's nothing there. So I know that this is the fault. So I can use that to narrow down on blockages of the signal, to find out where the signal changes. Maybe it becomes quieter than it should, maybe it becomes louder than it should, maybe it's becoming distorted. And then once I've found my area, then I can start troubleshooting individual components or replacing things. I tend to use that, not the AC voltage readings for analog signals. I could also use an oscilloscope. Obviously I can't hear it, but if I'm injecting a nice sine wave into a system and then it comes out a bit square, then that's distortion. If it isn't present at all, then I know that there's a faulty component, or if it's there but it's like really wiggly, then that's noise. So even for audio I could use the oscilloscope, and I guess for people who are working with like video signals that are analog or other kinds of analog signals, then an oscilloscope is a better option than an AC voltage reading, which is just a flickering number if you've got a DMM. So really the only AC voltage reading that's useful to me with a multimeter is situations where it's a steady enough signal so that like that number isn't going to flicker too much. So that means that I do have an occasional use for it if I'm trying to make sure that the playback amplifiers coming from a cassette player are all even, then I can use it for that, though I could equally use the oscilloscope. So really the only thing that I use it for is AC bias, which this is going to be irrelevant to most people who aren't actually working with tape machines, but bias is a very high frequency sine wave that is used to excite a tape so that the AC audio signals will kind of create a magnetic pattern on the tape. So it's used as part of the recording process, but just AC bias is thrown onto the tape in order to raise stuff as well. So it tends to be a fixed voltage, which is steady and doesn't change over time. So I can use that AC voltage meter to test for the presence of the AC bias and make sure that it's loud enough. But that ends up being really the only thing that I use AC voltage readings for. Everything else is kind of DC voltage and continuity testing for the most part. So let's start off with the continuity tester. So I'm pressing the mode button on this particular unit, and then I don't know if you can see properly, but there is, get a scrap of paper so I can draw it, but usually this suggestion of audio waves kind of symbol denotes continuity. And what continuity testing is a very simple yes-no test, like is electricity getting from A to B? And if it is, this thing will beep and it will show a resistance. So if I leave that for there, you can see that there's basically 2 ohms of resistance. That's really not very much resistance at all, because if you think some resistors that do pass some current have like millions of ohms, and values of several thousand ohms are quite common within circuits. And the way this particular one will work, it'll vary from meter to meter, but this one, it'll beep if it's less than 50 ohms. So what we would expect is that a wire, if it's intact, will beep. So if my body, it has too much resistance, right? That OL, I think it stands for overload. I think it's basically saying there's so many ohms that it's outside of the range of what this is reading. So the reason that this is important is you could argue that there's only 2 things that go wrong with like some audio electronics, and that is either electricity is getting to places it shouldn't be getting to, or it's not getting to places that it should be getting to. So one of the things that comes up really often is that solder ages and it stops connecting, or there was a dry joint when it was first made and it sort of worked for a while, but in the process of being moving around, it stopped passing current, or someone's dropped something, someone's left something unconnected, or maybe there's like a coil that's overheated and it's open, meaning like it's not connected anymore. So this is a way that we go around and we check that stuff that should be connected is connected. So before going on to the other modes, I'll give you a couple of practical examples of how I might use this. Here's an example of how we might use the continuity tester. Something that goes wrong quite often on the sort of machines that I fix, which are Portastudios. They've got a mixer built into them. Dust and dirt or even spilt drinks quite often get into the recess on the fader, and that can cause corrosion. Sometimes the little brushes inside here will break. I will be doing a separate video, by the way, with a much more in detail look at how these faders work. I'm just going to go over this briefly. So this fader is situated like that, and in that position it's got a very high resistance, it's out of range. But when I put that up, resistance drops to, well, it's about 12 ohms. And then when I turn it down, sound cuts out. So we can use this to test whether faders equally switches are passing signal or not. If we've got a dead channel in a mixer, we can find out using continuity tester whether an unhealthy fader is our culprit. Should say as well about testing faders. Faders are a situation where we can be confident that there isn't a parallel path for the electricity to go down. So we can usually test them in circuit, which is something that we can't reliably do with a lot of other components. So if I turn this over, the fader's up, it should have a low resistance. I won't go into in video exactly how to identify which pin is which, but I know it's this one at the top, rightmost, and rightmost in the bottom of these four. So if I touch those, I get continuity, and then I know that that fader is good. Here's another example of an application for a continuity tester, which is to ascertain whether any coil of wire is intact. There's a number of applications for a coil of wire. Here I've got part of a relay, so things I work with, cassette players, relay is part of the mechanical operation of the cassette player. So if the relay isn't working, I want to figure out whether it's the relay that's broken or whether the relay isn't receiving a signal. And so I can test for continuity. I've got the clips attached here, so when I plug this in, you can hear that that coil is intact. You can see it's got about 31 ohms. Another example of an item that has a coil inside it is the record playback head for my tape player. Now you can hear that it's not beeping, but there is an electrical connection there. It's just that it's 170 ohms rather than below 50. That's why it's not actually beeping. But we can tell, cause I'm getting that reading, that not only is that segment of this record playback head intact, but also the connection from this header to the wires and from the wires to the base of the head. The cables are all good as well. Here's another scenario. I figured out that there should be a signal coming in through the middle of these three wires, the red one, into this circuit board, but it isn't. So what I want to establish is there a break in this cable that I can't see? Is there a problem with this solder? So you can see I've got the negative connection. I've got this banana to alligator clip that's attached to a male to male DuPont wire, and that's going into the third pin there. So that's the red, the central one of these wires. The signal should be coming out to this point here. And it is. And that tells me that this cable and that solder joint is intact. Sometimes you'll have bad solder on the board itself, or there'll be a little crack that you can't see, or in some extreme cases heat damage will destroy the foil that's conducting. You know, this is green because it's got this paint that's non-conductive over the top of it. Underneath there, I mean, I'll go ahead and scratch this because this is a scrap board anyway, but if I were to scrape away at that, sharp enough. It's copper foil under there, but it's quite thin, so if there'd been a lot of current through there for some reason, then that could be damaged. So we can check that the electricity is getting from point to point on a circuit board using continuity tester. So is this strip, the lighter green, that's the copper foil, allowing current to pass? Yes, it is. A useful application for continuity testing can be to find whether things that should be joined to circuit ground are, or to find out if things are connected to circuit ground. So here I've got a Tetrakan Portastudios 424 Mark II. Here's my continuity meter inside, and a system like this, you know, you've got several different circuit boards, mechanical parts and everything, and really the largest metal areas, like the largest areas underneath the circuit board. So here's another circuit board. You see all these big areas of copper? They appear lighter underneath this green paint. They're all going to be part of ground, and then there'll be like a cable like this, or, you know, probably black one of this cable here, that's going to join up to the largest areas of copper on other circuit boards in the same system via cables like this. It's going to connect to large metal areas of this cassette player and so on. And you can test whether those are all connected correctly. I've got all the grounds here connected. So for instance, if I go from, you can't quite see there, but it's one pin of a slow blow fuse on this power board. If I go from there to the chassis, I know that they're connected to circuit ground. Usually the silver casing on these variable inductors or transformers, they're usually connected to ground, so yeah, so we can tell that this item in this board or this item in this board are connected. Equally, I get a beep if I go from the casing of this, I'm not sure if that's a transformer or a variable inductor, but anyway, from the casing of that component to that fuse, I also get a beep. The metal part of this LCD display, I know, the metal casing around it, it's connected to circuit ground, and so that connects up to all these other places. So essentially the 0 volt reference level, the place where the electrons go to die once they've expended all their voltage energy, they should all be connected. So sometimes if you get a hum in a system, if it's audio, there's an audible hum in the system, that's because the ground of all the different circuit boards aren't joined together properly. So you can use it as a diagnostic tool that way, continuity testing, to check all these things are connected. Or if later on you're going to be powering this separately, but you're going to be underneath it and testing stuff, and you want to know where to put the black probe while you go in here and measure voltages or resistances or something, then you can figure out, all right, yeah, that casing, what else is going to be a good bet here? I haven't really checked it, but I mean, there'll be various other points. I mean, like yeah, I've got a little beep there. Where was it? Anyway, I mean, with these integrated circuits, like there's going to be a pin that's ground. And so really, it should be that you can put like your black probe on any of the points on this board that are joined to circuit ground, and then move this probe around and take measurements. The next most common setting on the multimeter that I would use after continuity tester is to test DC voltage. Check that integrated circuits and other active components are receiving power. That's one of the first checks I want to do if there's an electrical problem, is to make sure that actually the operational amplifiers is a component that comes up often in the kinds of circuits that I'm working on. So I want to check that the operational amplifier is actually getting power. If it isn't, then there might be an issue with a fuse, there might be an issue with the power supply, and I want to attend to that before I try and figure out why signal isn't getting through. So I've just got my probes, the red and black ones that came with the multimeter. This board is a faulty board. It's from a Tascam 44 Mark III. And although it's faulty, it does power on. So at the moment, power is off. Where do you put the black lead? That seems to be a common cause of confusion. The black lead should be put onto circuit ground. Circuit ground on a board like this can be assumed to be any of these big islands of green. These big islands of green, there's going to be jumper wires. I mean, you can actually see this one that I've highlighted with black Sharpie. There's an adjacent one there. And you can see that there's those are both pins, but on the other side there's actually a jumper wire, so that these islands are all connected. So those together represent the largest metal surface in the circuit. So they are circuit ground, and then one of the cables that joins this to the rest of the system will be joining to the largest metal areas in the other circuit boards, and that will be joining to things like the metal chassis and the cassette player. And so all those things being joined together represents like a large metal mass, and it's like where electrons go to die. And when we're making a voltage measurement, we're really measuring a difference in potential between circuit ground and the pin of a component. So with this power off, I should be able to put the black probe onto, I'm choosing that, but here's a big green area here, so that pin's set into it, so I could use that instead. I've just highlighted this one. And then just to the left of this black streak here, these are the 8 pins of an op amp. I go down those now with the power off, then I should get readings that are either 0 or very, very small. The difference in electrical potential and electrical pressure between this point and this point is 0. Then if I turn the circuit on, and I start to get readings. So I mean, that's almost 0 there. 1 volt here, almost nothing there. This one that's about minus 5 volts. What was the other one? Plus 5 volts. So we can see that that's got, that's probably the positive 5 volt power supply, and that's the negative 5 volt power supply. So you're getting, well, it's a bit less than, somewhere between 4.5 and 5 volts. So it's giving us about 9.5 volts of swing. That's how much AC signal that op amp can process. But really all I would be doing is like looking at the serial number of that operational amplifier. You can get the specification sheet off the internet for these things really easily, and it will usually tell you what power supply it should be receiving. And if on those pins you're not getting that voltage supply, or it's like wildly different to what it says in the specification sheet, then you know you've got a power issue. So check that active components are receiving the DC input voltages that they require in order to operate. Here I've got my faulty 44 Mark III board turned on again, and there's two similar looking transistors here. I'll show you a couple of things about how we can use direct current voltage measurements to see what's going on there. If I put my black probe onto this pin that's in the middle of this large green area, I can assume that that's circuit ground. And here's 3 pins of the one of those transistors just beside my red probe here. So what are the readings? About 4.9 volts, about 8.5 volts, about 5.5 volts. So one of the things I can do is compare two transistors, say they were the same or very similar transistors, then the readings on them should be pretty similar. So the 3 pins of the other one are up here. The readings I'm getting are nearly 0 volts, nearly 0 volts, and nearly 0 volts. So let's say for argument that this existed in a healthy channel and this existed in an unhealthy channel. I'm actually in the power section of this board, but say that those components were in channel 2 and channel 4 of a mixer, and I knew that channel 4 was healthy and channel 2 wasn't, then that might be an indicator that the fault is somewhere around here. Now in this case, the reason I'm getting such different readings is that I've actually removed some components in order to repair another board. You can see there's a missing transformer here, there's I can't remember what I removed from there, so that'll be why that's not getting any power. So this whole thing where you do A/B comparisons between a healthy and an unhealthy channel using either direct current voltage readings or resistance readings to find which parts of two identical channels of circuit differ. So I mean, this would be a common thing with the left and right side of a home stereo unit. If one side's working, the other isn't, then the readings on the healthy channel should be the same as the unhealthy channel if that part of the circuit is healthy. And once you found a section where the readings are different, then you're closer to the sorts of components that you need to replace, right? And the other thing that can happen, if we go back to this transistor that's still getting correct readings, you'll notice that these numbers 4.5, 8.5, 5.5, they're all like significantly different. Like they're at least a volt different from each other. Say 2 of those readings were both almost exactly the same. They were both exactly 5.5 volts. That would indicate that there was a short in that transistor. Like basically, instead of there being like a semiconductor relationship between 2 of the pins, it's like there was just a normal piece of wire. And shorting is quite a common failure condition for semiconductors. Like if they get too much current for some reason, then they burn up and they effectively just become a piece of wire. And that can lead to things like the power supply sending a lot of power straight to ground and other parts of the circuit not working. So that's kind of a quick and dirty way to figure out whether semiconductors aren't, if the voltages at more than one pin are too similar, then that can be a bad sign. But really what you want to do is desolder that and take it out of circuit and double check it for voltage drop, which will be in the next section of this video. Right, next up, using the diode tester to test diodes and transistors. So I want to be in this mode here. If you can't quite see that properly, it's this symbol. That's the symbol for a diode, okay? Diodes and transistors are semiconductors. There's loads and loads of videos about how those work, how they're made. I'm not going to go into that just now. What I'm going to say about them is that they tend to be, in Portastudios, like a passive component that are like a supporting cast for things like operational amplifiers. You can use transistors as current amplifiers. We don't tend to see that in Portastudios. They tend to be used more as like switches. Diodes you see in support of switches, making sort of one-way networks around, like, choosing buses and stuff. Obviously there'll be like rectification applications in linear power supplies. If all of that sounds like gobbledygook, then don't worry about it. Key things: a diode is like a valve, and a transistor is like two diodes, but they're sharing one leg. So like if I draw that, here's a diode, here's a diode, and they're sharing one leg. So you know how to test a diode, then you know how to test a transistor, because it's really two diodes joined together. What a diode does to the direct current, it's a bit like what a valve does to water. A water valve should allow all the water to go in one direction and none of the water to go in the other. If it's faulty, it can fail in three ways. One is that it allows water to go in one direction and the other, in which case the valve may as well not be there. Or it can stop water not only from going in the direction you want to stop it to, but it actually stops water coming out as well. It may as well be the water pipe's disconnected in that case. Or you can have a valve which is allowing water to go in one direction, but sort of allowing it to go less, but a little bit in the other, so it's leaky. And these are the three ways that a diode can fail. You can have it so electricity is just going in both directions, like it's a normal piece of wire, so that's called shorted. You can have it so electricity isn't getting it through it in either direction, so that's called open, as though there were an open switch. Yeah, so two bits of metal touching, it's open switch. Electricity doesn't get through in either direction. Or it can be leaky, which means that the electricity goes through in one direction, but it also goes through in the other when it shouldn't really be able to get through at all. And the characteristics of this are, if you're using your diode tester, then you should get a voltage drop of about 0.5 to 0.8 volts in one direction. That's the direction it's allowing electricity. And then it should say OL like this, which I think is an abbreviation of overload, like these aren't touching in the other. So let's test that now. I know that this is healthy. I tested it off screen. So in that direction, nothing's getting through. In this direction, I've got a voltage drop of 0.5 volts. So that is correct behavior. We're getting voltage drop in one direction and it's not passing any voltage in the other. Now let's have a look at this transistor, and we just need to treat the pairs like these two are a diode and these two are a diode. So this one, so we've got nothing in that direction. Swap the probes round, and we've got a voltage drop of just under 0.6 volts. So that half of it, that diode within the transistor, is working correctly. Let's look at this pair. This direction, 0.65 voltage drop. Swap the probes over, and yeah, we've got nothing. If you've basically, through deduction, you've got a rough idea of how the circuit's working, and this particular part of the circuit, this particular function isn't working, and you've either looked at the circuit itself or the schematic and you figured out, all right, there's a diode in there or there's a transistor in there, maybe that's the problem. Can you do these tests in circuit? Yeah, you can, but sometimes the way that these are wired in, then there are parallel paths. So it's not really reliable to do the test in circuit like that. I would rely on those sorts of results with a pinch of salt. Ideally, you do want to desolder them and test them out of a circuit like this. But what I'm going to tell you is that if you've got the trouble of taking them out, and you can afford another fraction of what this thing costs, you can buy one of these things. And for instance, if I just plug this in, shut it, and press the button again, it's going to tell me that it's an NPN transistor and tell me which pin is which. Okay, if that was faulty, what it would say is it would only show 2 pins. It would show a diode there, you know, say that was closed. So in a way, this is kind of more convenient. Likewise, if I press that and it's like, oh, it's got nothing in it. Yeah, no unknown damaged part. And then what I can do is I can plug in this diode. Yeah, I mean, I've got it going from 1 to 3, but yeah, it's showing me that it is a diode. If that was open, if I use this DuPont wire, then it's just showing that as a resistor. So if you put in a diode and it showed up as a resistor, that would show that it was open. If you put in a diode and it came up as no unknown or damaged part, then that would show that it was open. I suppose that unless you know how to interpret things like these parameters, it might be a little bit difficult to tell from this reading that a component was leaky. And in that way, using the diode tester on this is maybe a slightly more reliable way to understand that third and subtler category of failure. But yeah, a lot of the time I do find myself using this rather than that. I mean, if I'm confused by the result of something, then I might go back to that, but that's how I use the diode tester. So there's a capacitance mode there. I mean, that would necessitate taking the component out of circuit, and again, I would use like a very cheap tester like this. Like if I put this capacitor in here, it not only will tell me the capacitance, but it will also tell me the equivalent series resistance. So, you know, I would tend to use that and not the meter if I needed to do that. But these are fairly cheap and they're fungible parts and they fail quite often. So once I've honed in using my audio probe on a section of a circuit where I'm like, well, the problem's here. If there's electrolytic capacitors in there, for the sake of taking maybe a couple of minutes per capacitor to change them over and spending maybe 30 pence per capacitor to change them, I would just tend to put in new ones. I mean, although the life expectancy of the Japanese made ones before the 1990s is good, you're still getting an extra 20-30 years of life into your machine by replacing them. So yeah, I would just tend to replace those without bothering to kind of agonize about what their equivalent series resistance is and so on. If you've already eliminated the sorts of components that fail more easily, which I would say are anything with moving parts like faders and potentiometers, electrolytic capacitors like this, it's a seal with some sort of liquid in there, and no seal is perfect, so sometimes they will just fail. Not a lot of them, they tend to be pretty durable, but if you've got several hundred of these in a Portastudio, it's not all that rare for a handful of them to be leaky. So if you've eliminated all those sorts of parts and something's still faulty, then you could take your resistor out of circuit like that and go into resistance modes and check that the value is actually what it says. Because sometimes if these have been subjected to a lot of current, then yeah, so 85 kilo ohms is correct for that. But usually they would look heat damaged if they had so much current through them that the value of them had actually changed. So you can do a thing, but we can also do it with the voltage DC, where you can test a healthy channel to an unhealthy channel if you've got a mixer and see whether the readings are different, to help you diagnose which component is faulty. But you know, again, I find that the audio probe is better for finding that. I might be leaning on like resistance and DC readings, comparing a healthy channel to an unhealthy channel in order to find where in a circuit the fault lies if we weren't dealing with audio signals. But because I can use the audio probe to listen to where the sound stops or changes, then that usually allows me to hone in on where to start replacing components, hoiking them out and testing them individually. So again, yeah, I don't really use that resistance setting very much. I mean, you could use the resistance setting if you didn't have a continuity meter, if you had like a really simple or really old meter with no continuity setting. I suppose you could use it for that. Right. Under what circumstances might I use the AC voltage meter? Well, I suppose the regular thing that I use it to test for is whether the AC bias is reaching magnetic heads. I will cut in footage from a video I made recently where I was testing the array system on a Tetrakan 488. That was a ranging glitch there, but yeah, now you can see it's 0.54 volts RMS. So the peak voltages in the positive and the negative direction will be higher than that, but the average voltage is about 0.55 volts or 545 milliamps. As you saw earlier, this is track 8 that I'm plugged into. Track 3, that's the faulty one, is in this plug over here. So if I go and plug in there instead, got pretty much 0 volts. It's probably just it's background noise or something that's reading. And if I go to, I did this off screen, this is why I know this. The frequency counter isn't picking it up. So that means that the bias signal isn't getting as far as that socket. I might also use it to compare the output level from the tape outs when I'm doing the calibration of record and playback amplifier. So here you can see I've kind of partly stripped this RCA cable so that I could attach my alligator clips here. So, you know, I can use that to eyeball whether the output, the, sine waves that are coming off like a TAC test tape like this are equally loud from all 4 of the tape outs in a 4-track. Quite often I would use this instead, just because, this kind of connector that you use for oscilloscope probes, I've got this adapter, so I could just use an RCA cable directly coming out. I'll cut in some footage now as well, showing how I would actually test the frequency that's coming from the test tape and the amplitude at the same time using the oscilloscope. So with the tape running, I'm just gonna go to the 4 tape outs, check that visually all of them are the same sort of amplitude, which it looks like they are. Maybe a couple of them are coming, the peaks are coming out of the screen a little bit, so I might turn them down very slightly. So you can see by turning that trim pot I pointed out earlier, I can adjust that. So I'll get it so the peaks of each channel just come up to just below the top of the screen there. I could use the meter for that. If you had the meter but not the oscilloscope yet, then at least that AC voltage meter would allow you to be doing those kind of calibrations. I don't tend to find myself using the AC voltmeter in order to test for the presence of AC voltage within the power section of Portastudios, because either that is being dealt with in an external power supply. When we say an external power supply, I really mean something like this, and there's either a transformer, like an actual transformer, or like a switching power supply inside a wall wart like this, and then there's like some sort of coaxial cable that's going into a socket in the back of the unit. If there is a linear power supply inside the unit, so like, here's a 424 Mark II, and it's got an internal linear power supply, so the actual transformer, I wouldn't be touching it like that, by the way, if I wasn't absolutely certain that it's unplugged. I suppose you could use it here to test for the presence of AC, to make sure that, the AC that's coming in via this cable is like, getting to the primary side of the transformer or out the other side to the secondary side of the transformer. But, you could actually use continuity tester with the unit turned off to check that coil was still intact. These diodes that are being used for rectification, there's 4 of them down here. I don't know whether you can see that because of the light, but you can use the diode tester for that. So there's other ways of testing everything that's there without putting your probes near quite a high level of AC. Okay, frequency counter. I'm back with the faulty 424 Mark III board, and down here we've got the master oscillator. You can see this is at 0 hertz at the moment. The casing of this is going to connect to circuit ground, And there's a little pin here, it says TP. Actually, the little, that stands for test point. And that's the test point for this, which is where I would put the positive pin, but you can actually see it's empty. It's broken off, but these two jumper wires are going to it, so I can put the red pin there instead. So if I put the black one there, so it's saying it's 60 hertz or something, it's just hum, but I put that on there. There we go, 84.64 kilohertz. So it's meant to be 85 kilohertz. So you can see that the bias, AC bias, that is part of the record function and all of the erase function, is working correctly. If I want to adjust that, then I would turn that little magnet in there, and that would change the frequency. Right, absolutely winged this one. No preparation, no scripting. But I'm probably going to give myself a bit of a headache in the editing for that reason, but I hope that's kind of helpful. If you feel like there's stuff I didn't cover or the stuff I didn't make clear, then let me know in the comments, and maybe at some point in the future, using those comments and the shortcomings and transcript of this video, I can sort of like carve out a more effective video in the future. But I just thought I would, since I didn't really have a video up on this channel about using the meter, then I would make this. Right, I'm really burbling now. Thanks for watching. Hope to see you again soon. Bye.